Okay. So we are term 3, week 1, Friday afternoon. Hope everyone's doing well. We've got a cheese of a lesson today, normal distribution. Nice and easy, something we've seen before. And then hopefully get some folio time. Now it's split up into 2 parts because 8C focuses on normal distribution, just using our understanding of the bell curve without technology, and then 8D is normal distribution but using technology. I'm going to teach both at the same time. So let's just have a look at our notes here. The first box there, I just want to point out the normal distribution function, okay? That's the function there. The only variables you would put in would be the standard deviation and the mean. And you could graph the bell-shaped curve on the x-axis, okay, on the Cartesian.
What page?
Oh, sorry, 19, page 19.
I think we've got different pages.
For the stats book?
It just doesn't
Oh
look
my
the same.
gosh, what's going on? Statistics notebook. What's this, the old one or something? How old is this, I wonder? Cool. Okay, so I'm just looking at where it says the normal probability density function in bold. Okay, I remember now. It's the same. I just converted it from the textbook box to text. So it says the exact same thing. Okay, so I'm just talking about that function of x. That's the normal distribution function, and you could graph that on the x and y axis. Okay, the only other thing to say, it's a probability density function, which means the area under the curve is 1. The result is bell-shaped. And normal distribution is fascinating because basically everything that you can measure is normally distributed. Okay, so height, weight, head circumference, distance from your elbow to your head, basically everything is normal distributed. Where you have the mean, okay, that's the average result, and you have 50% of results are larger than the mean, okay, and 50% of results are lower than the mean, okay, so basically you can say, 50% of people did better than average. All right, 50% of people did worse than average. And funnily enough, this is a really funny thing about human beings. When you ask people to rank their competency in their workplace, so like as a teacher or maybe you're good at making burgers at Hungry Jack's or pizza at Cosmo or something like that, when they say, how good are you compared to your co-workers? Okay, you have 90% of people say they're better than average. Which is not possible based off of our normal distribution. All right, so let's get into our example. We have given x is normally distributed. This is like some notation. Remember, you maybe reflect on that from binomial distribution. We had, so I go back to chapter 7, we have x is some variable. It is binomially distributed with number of trials and probability of success. So we're going to contrast that with normal distribution, okay? N for normal, B for binomial, and we have the mean and the standard deviation squared. Okay, that's how we state it. So for our example here, we're given some variable is normally distributed. We have a mean of 30 and a standard deviation of 5. To give it some context, let's say that this is the length of bream fish in the Glenelg River. The mean is 30 centimetres and the standard deviation is 5 centimetres. Okay. So that's given the function at the bottom. Let's go to the first problem. Find the probability of 30 being less than x being less than 35. Okay, so what this means is what's the probability that a fish will measure between 30 and 35 centimetres? So we're just going to answer this straight off the bell curve. Okay, so we have the mean always in the middle, and we're going standard deviations above the mean, standard deviations below the mean, between 30 and 35, because the standard deviation is 5, right? So I've got the mean is 30, 30 plus the standard deviation, 30 plus 5, 35, that's going to be my next line. My next line would be 40, that's how I've generated this curve here. All right, and all normal distributions occur such that 34% of the data occurs between the mean and the mean plus 1 standard deviation. All normal distributions are going to mirror that. So our answer here is 34.13%, okay, or we can state it as a probability. Now, maybe I'll just talk about some notation because there's a number of ways that we can state things, isn't there? You often hear these words, what percentage, what proportion, and what's the probability. So they all the triple P's we can think of. Okay, so probability is a number between 0 and 1. All right. Percentage is a percent value. All right, it's the decimal, it's the probability multiplied by 100 with a percent on the end. Here's your percentage. And proportion, we'll accept either. Okay, what proportion? 34%. What probability? Yeah. So both of those are correct ways of expressing the answer. Okay, next one. Find the probability of x being less than 22. Now, for this one here, if we're going to look at our curve, we don't have 22 appearing on the curve. In fact, the next number down here would be 15, and 22 is going to be here somewhere. 22 is going to be there somewhere, isn't it? So if we're asked the probability of x being less than 22, what it wants this area under the curve. Now, the best way for us to do that is just in our stats mode in our calculator. So I'll take you there. Because it doesn't coincide with one of the bell shapes, we have to use technology now. So in here, we have 8C, now we're moving on to 8D. So you just go to your menu, statistics, distribution, normal, and NCD, okay, for normal distribution. And just like binomial distribution, you can perform these calculations in RunMat as well, just like we did with binomial. So it's really up to you where you do it. So distribution, normal, NCD. Make sure your data is set to variable as well. And you'll have these things to input: the lower boundary, the upper boundary, the standard deviation, and mean. Well, in our circumstance, we know the mean, we know the standard deviation. And so then I'm looking at my bell-shaped curve here, and we're told it has to be less than 22. So that means if I'm calculating this boundary, 22 is the upper boundary, isn't it? So I'm going to put 22 as the upper boundary. Now for the lower boundary, we're not going to put 0, we're going to put negative infinity, okay? We just put the biggest negative number we can, okay? Now the way you type that in, minus, most of you have the times 10 now, times 10, 99. So our lower boundary, minus 10, 99, 10 to the power of 99, upper boundary 22, standard deviation 5 mean. All right, we evaluate this, we get 0.05479. Okay, 4 figures, round the 4th figure, 0548. Very good. Part B. Part C, find the probability of x being larger than 28. Okay, so we're in the same mode. 28 is going to be here somewhere. So, who wants to have a wild guess? Is my answer to this going to be larger than 50% or lower than 50%? It has to be larger, right? Because we know that from 30 onwards, that's 50%, and then we're going to add this little bit to it as well. Okay, so our lower boundary is 28. Our upper boundary this time is positive infinity, okay? Because we're going all the way that way. So this time we just type in the same thing, except we don't chuck the negative in front of it. Okay, we just want positive infinity. Standard deviation and mean remain the same. And if we evaluate that, we get 65.5%. Oh, let's write it up as a decimal, 0.6554. Okay, now last one. Find 1, evaluate 1, take away the probability found in A, found in B, take away the probability found in C. So it says 1, take away the probability of x being less than 22, take away the probability of x being larger than 28. Okay, so if we evaluate that, what we have is we have 1 is the probability of all events, Take away this event, probability of x being less than 22, we saw was 0.0548. And then take away the probability of being larger than 28, we saw was 0.655. Okay, so if we evaluate that, we're going to get 0.2897. Okay. Might be a little bit different because I haven't typed that into my calculator. Who wants to guess what I've typed in?
Lower boundary 22.
Very good. I've typed in this statement, probability of 22 being less than x being less than 28. Now, why would we anticipate that these are the same? Okay, this one is all probable events, 1, all probable events add to 1. Take away the probability of it being less than 22, take away the probability of it being less than 28. It's going to leave you with this area, which is the same as this calculation here. Lower boundary 22, upper boundary 28. So that's all I've done, typing in. I was a little bit lazy there. The result says confirm that they're the same. Okay, so they should be very, very close. If there's a slight error, it's due to us cutting the decimal places short for both of these. Okay, so that's pretty much normal distribution. That's what we're doing here. We're applying it in the context. What does it mean? Okay, so here if we have a fish, you know, fish are 30 centimeters long. Here the probability of catching a fish that's smaller than 22 centimeters is, you know, 0.0548, 5%. And like normal distribution is fascinating as well. I didn't say this before because most of your results are centered around the mean, and the further away from the mean you get, so like the taller you get or the shorter you get, the more, the further away from the average you become. And the lower that probability is, right? Most people are average height. You do have some people, you have a small amount of people that are really, really tall, a small amount of people that are really, really small, but most people sit around average, hence most of the probability congregates around that region. Okay, let's do it. 8C, 8D, folio, up to you where you direct your efforts. Let's get into it.